Thanks for coming to the talk. So this is Joey work with Tim. And so the starting point of this talk goes back more than a century to Brouwer's fixed point theorem, which states that every continuous function that maps the closed disk to itself has at least one fixed point. So it has one point which has remained intact under the mapping. And over the years, as probably many of you know, this theorem and its many generalizations, such as the Borsa-Coulomb theorem and the Kakutani's fixed point theorem, have had a profound impact on many subfields of mathematics, geometry, logic, and perhaps most of all on economics and game theory. To give just one example, essentially all known existential proofs of equilibria in finite games rely on reductions to such fixed point theorems. And therefore, you might find it as no surprise that this was the original motivation of this work itself, but we'll get to that towards the end of the talk. So Brouwer's fixed point is non-constructive, right? It's an existential statement, and it's natural to ask how hard is it to actually find a fixed point guaranteed by this theorem. And indeed, due to the basic nature of fixed point problems and their applications, a long body of research, a long line of research was devoted to the algorithmic question of computing fixed points. So some of the earliest and perhaps most well-known algorithms for this problem were proposed by Scarf, later generalized by Lemke and Hausen, who showed that it is possible to find a fixed point of an n-dimensional manifold mapping the n-dimensional solid cube to itself in time exponential in the dimension n. And fortunately, we do not expect to find significantly faster algorithms for this problem. And in fact, this problem, or essentially a discrete analog of it, turned out to be almost by definition a complete problem for some subclass of total search problems known as PPAD. And this naturally led to, as we often do, to a relaxed notion of the problem, focusing on the more modest goal of computing a point whose displacement is not zero, but some small value epsilon, possibly subconstant. And for high-dimensional manifold, it turns out that the right proxy for this is the L-infinity norm. So I'm not going to get into this, but this is motivated by applications. And unfortunately, even computing approximate fixed points is a hard computational task, at least for subconstant values of epsilon. And for the constant epsilon regime, we have a good understanding due to a very recent work of Yad Rubinstein. And the bottom line here is that, at least in the white box model, where we're given semi-explicit access to the function f, the approximate fixed point problem is fairly well understood. So another model in which fixed point problems were studied is the other extremes, the black box query complexity model. So in this setup, we're given an implicit access to n-dimensional manifold f, H, that's mapping the n-dimensional solid cube to itself. And this function has some absolute constant Lipschitz factor, which you should think of as 100. So it's an absolute constant. And we have implicit access to this function, so we can query it in interior points x and get back the displacement f of x. And of course, the question is, how many points do we need to see until we recover a fixed point of this function, or more modestly, an approximate fixed point? It's not hard to see that in one dimension, the problem is actually easy by some binary search. More generally, in any dimension, if the Lipschitz constant is smaller than 1, so if f is contracting, the function, again, the problem is easy because you can just iterate log 1 over epsilon times and find an approximate fixed point. So what happens for general dimensions? And the answer was given in a beautiful paper in the late 80s due to Hirsch, Papadimitriou, and Vavasis, who showed that, for any dimension greater than 2, there is a family of very explicit Lipschitz functions, so 72 Lipschitz functions, such that finding a 0.01, say, fixed point of this of a given member of this family requires exponentially many deterministic queries in the dimension. And this result was recently generalized to the randomized query model. Let me just tell you what's kind of the heart of the HPV result is a geometric embedding that allows to take an exponentially long discrete random walk on the discrete cube. So this is a purely combinatorial instance. It allows to compile it, so to speak, to interpolate it into a continuous function that mimics this walk. So I hope you can see this function. These are supposed to be arrows. Hopefully you see the pattern of the random walk. So it allows to take a completely discrete random walk of exponential size and to embed it into a function that mimics this walk in a way that the unique fixed point of this interpolated continuous function corresponds to the endpoint of this walk. And more generally, for small enough approximation parameter, any approximate fixed point will recover the endpoint of this walk. Okay, so at this point, the lower bound boils down to the level of an exercise because the mixing time of a random walk is so fast that if you don't keep track of it by querying it sequentially point after point, you'll be walking in the dark in no time. So this is essentially the result. And I'm not just telling you this for fun. This will come up in a talk recently. But the bottom line here, the story so far, is that at least in the black box and white box models of computation, we understand the approximate fixed point problem pretty well. Okay, so our paper kind of initiates the study of distributed fixed point computation. So we study the problem in a gray box, so to speak, model. Right? And indeed, communication complexity is often viewed as this intermediate model of computation where each party gets some explicit information that it's arbitrarily allowed to manipulate, but it's only partial information on the world. So it's some gray box model. And when you think of it, it's not even clear how to define the communication complexity version of computing fixed points, because presumably there are many ways in which we can distribute the inputs among the players. So the communication version we suggest, and we will argue is both natural and well-motivated, is the following. So in this setup, Alice will receive an explicit function f mapping the n-dimensional cube to itself. And just to make things discrete, we're going to talk about the communication complexity model as a discrete model. So we're going to talk about bits and so forth. We would like to discretize this input. So we will evaluate this function on some finite discrete grid of granularity alpha. So you can think of it as Alice receiving the truth table of this function. So the truth table will have exponential size, right? Something like 1 over alpha to the n. But the important thing is that this function has structure. So the maximum distance between the image of any two neighboring points is at most some fixed constant, let's say 100, some fixed parameter lambda 1 times the distance in the domain. Okay, so this is not an arbitrary function. It has a lot of geometry. And you might guess that Bob will receive a similar instance. So he receives a function g that's mapping the solid n-dimensional cube to itself on the n-dimensional alpha grid. And this function is also lambda 2 Lipschitz. And what is their goal? Well, you want to find a fixed point of the composed function obtained by concatenating the green arrows to the black arrows. So the black arrow is the displacement of f, and then g. So where's the fixed point in this picture? Well, it's here, right? So you can see that marginally this point, this red point, doesn't look like a fixed point for neither of the parties, but somehow this is the answer. And so we denote this problem as AFPC, approximate fixed point of composition. The communication problem of finding an epsilon fixed point of this structured instance. Make sense? Okay, so you might think that that the communication complexity of this task should vary both with the geometry of the problem. We already saw that if lambda 1 and lambda 2 are smaller than 1, the problem is easy. The players can just iterate the function and find fixed point. And of course, with the approximation parameter epsilon. So what should be a natural choice for the approximation parameter, for the approximation quality? So what I claim is a natural choice for it would be the product of the Lipschitz constants times the granularity of the grid, alpha. Why is that? Well, this is exactly the cost of rounding an exact fixed point of the continuous extensions of these functions on the grid. So if you take these functions, you extend them using Lipschitz extension to be continuous on the entire solid cube, Brouwer guarantees there's an exact fixed point, right? If you take this exact fixed point and you round it back on the grid, this is exactly the accuracy loss that you'll lose because the function is smooth. This is where the Lipschitzness comes into play. Make sense? Okay, so another interesting or challenging, depends how you view it, feature of this, of the problem for this value of epsilon is that it has a very low non-deterministic communication complexity. Basically because there's always a short certificate for a solution, namely just Merlin can just tell Alice and Bob the name of a point, and they can very cheaply verify that indeed it's a fixed point. So, this should insinuate that proving lower bounds for this problem is not going to be easy because there's non-trivial things going under the hood here. So our main result is a lower bound for a promise version of this problem. Namely, we prove that there are constant grid size and Lipschitz parameters such that finding a lambda 1, lambda 2 alpha over some absolute constant, 43, indeed requires exponentially many bits of communication in the dimension, or in other words, a polynomial number of bits, some n to the small delta in the input size. Okay? And what makes this statement interesting, even though it's a promise version, is that the theorem holds even under the promise that the composed function, or rather the extension of it, the continuous extension of it, is a continuous function. So the Lipschitz constant of the composed function will always be some absolute global constant. Okay? Intuitively, this continuity of this promise imposes a lot of structure on the problem that presumably Alice and Bob can exploit, right, in their communication protocol. And this is what makes this theorem non-trivial. And indeed, if you ignore this condition, then you can prove this lower bound essentially by a fairly simple, straightforward reduction from set disjointness. So this thing adds a lot of geometry, another kind of geometric aspect to the problem, which is somewhat new to communication, to the basic combinatorial nature of communication problems. Make sense? Okay, so I'll just mention that we have also an analog of this theorem for the multi-party number in hand setup, where each player will receive a scalar function, a scalar Lipschitz function. Okay, and then the goal is the same. They want to compute the approximate fixed point obtained by composing their functions, but I'll focus on the two-party version. So kind of the heart of our approach, or the basic technique in which we use to prove the lower bound, is called lifting, which is, morally speaking, a technique that allows to convert lower bounds in the simpler query complexity world into two-party communication lower bounds. And this technique was very successful lately in proving many separation results in complexity theory. So the basic setup is that we have some arbitrary search problem, S. And this problem receives capital N inputs over some arbitrary alphabet sigma. And we can take this query problem, right? This is a legitimate instance to a query problem. And we can generate a two-party communication problem from it by taking each input and splitting it using some carefully chosen gadget G between Alice and Bob. So each coordinate will be split in some carefully chosen way using some small gadget G, so that if Alice and Bob compute G, they evaluate the input and then they can proceed. And this gives rise to a composed communication problem, a totally legitimate two-party communication problem of solving the distributed version of the search problem S under this splitting G. Is that clear? So kind of a canonical gadget G. So the point is that the gadget here plays a crucial role, and kind of a canonical gadget, in some sense universal gadget that was proposed in the literature, was the index gadget. So here, Bob will receive a huge array of size polynomial in capital N. So it's really huge. And this array is filled with garbage, values, but somehow in the middle, the true values are hidden, and Alice will receive for each input I an index pointing to the ith input. Make sense? So, the first index is here and so forth. Of course, neither of the parties know this input because Bob just observes a bunch of garbage values, right? He doesn't know where the true inputs are hidden. Okay? And a beautiful result of Rosen-McKinsey from '99 that was extended last year to the more general setting. They proved that for any search problem S, the communication complexity, the deterministic communication complexity of solving the distributed version of S under the index gadget remains essentially as hard as the query complexity. So Alice and Bob cannot cheat. They cannot beat the trivial simulation. And indeed, the other direction is simple because they can always simulate any decision tree. Okay, so the only problem with this theorem is, of course, that if you take an arbitrary search problem S and you lift it using the index gadget, what do you get? You get some artificial problem. You get some weird problem. And our main observation, I'll have very little time to say, is that actually when you plug in the search problem to be the HPV function, the approximate fixed point problem, so each coordinate is the displacement of the ith input or the input x, you don't get an artificial problem. You get a very natural problem. You get exactly the approximate fixed point problem. It's really just a matter of 2 minutes of verifying. So I claim that if each input is just the displacement of x, and we view Alice's index, table of indices, as the truth table of some function mapping, mapping this space into G, and we view Bob's huge array as another truth table of some other larger dimensional function, then the index gadget, y of x, encodes nothing else but the truth table of the composed function, G composed on F. Okay, if you look at it after the talk, it's a matter of a few minutes. This is a really simple but key observation. Okay, and you might think, okay, great, so we're almost done. We can just apply the Rosen-McKinsey lifting theorem or not, right? So the main challenge, of course, is that Rosen-McKinsey is a completely combinatorial statement. It doesn't guarantee anything on the smoothness of this decomposition, right? Unfortunately, I won't have any time to say anything about the proof. Just maybe keep this picture in mind. What we do essentially is we adapt the Rosen-McKinsey theorem into geometric setting by taking each array and embedding it as a local code at the expense of blowing up the space by a constant factor of dimensions. And this ensures, morally speaking, that the index function, the indices encodes not only a Lipschitz function, but a bi-Lipschitz one. So even the preimage is Lipschitz. This facilitates the Lipschitz condition on Bob's side. And let me stop here with the technical parts because it wouldn't make sense, but it's essentially an adaptation of the Rosen-McKinsey theorem plus some, Lipschitz extension theorems. Let me just end by, the motivation of this work. So the initial motivation here was to study the role that interaction plays in distributed economic scenarios. And indeed, economic scenarios are in some sense a classical fit to communication complexity simply because valuations of players are private, right? So, and this line of work promoted by Hardin Mansour and Noam and several other people, the goal was to understand in particular the prototypical question of how long does it take the market to converge to equilibrium. And a prototypical problem, you might guess, is the simplest setting. Alice and Bob have payoff matrices to some, n by n payoff matrices, and they want to compute a Nash equilibrium of the resulting game. Okay? And note that the communication complexity distills the information theoretic bottleneck of this question, regardless of anything else. And the trivial answer is n squared bits. Alice can just send the matrix. Unfortunately, the exact problem does not admit any faster solution, but there are highly non-trivial things you can do for the approximate case. Using very little communication, you can find approximate Nash equilibrium. Our second theorem is that, I'm running out of time, so I'll just say it. If we would have proved a slightly smoother version of our lower bound for the total version of the problem, then this would imply a lower bound for finding essentially, a polynomial lower bound on the number of bits required by any protocol that finds some intermediate approximate Nash equilibrium. Okay? Unfortunately, we were not able to do that. But in a very recent, very nice result of Babichenko and Rubinstein, they adapted our lifting approach using much harder work of some algebraic and geometric machinery. Let me just end by saying that, morally speaking, the bottleneck, the challenge in our proof was implementing, opening the Ross-McKinsey box and implementing it with some geometric constraints. What Babichenko and Rubinstein did, they pushed the geometry to the reduction level, to the decentralized reduction to the Nash problem. This allows them to apply the Ross-McKinsey, so they strip down the geometry from, they're left with this random walk, this purely combinatorial instance. This allows them to apply Ross-McKinsey in a black box fashion, okay, and even a randomized version of it. So that's it. Let me just mention that the problem, their work does not answer the total search version of our problem. So this problem is still open. And of course, the natural question is, can we have a slightly smoother lifting theorem of Ross and McKinsey? And this question is still very much open. Thanks. Oh, yes. So I should say, so one could ask what can be improved in our theorem? Why is there hope to even prove a smoother version? And I guess in one line, the hope is that our proof actually exploits a very weak property of this HPV construction. It exploits the fact that the input to the query problem, this random walk, it has bounded displacements. So no point gets thrown off too far away. While this instance satisfies a much stronger, a global property. It's Lipschitz. It's a global property. So presumably you could exploit this in the Ross-McKinsey proof. The problem is that once there's some contradicting technical challenge, the Ross-McKinsey proof, it requires independence of each of these coordinates. And this conflicts with the Lipschitz property. So the question here and the hope is to combine those things. Can you combine those things? So it's an interesting question that interleaves combinatorics and geometry, and I'm still hopeful about that.
Yeah, you have a question.
Sorry, so the communication class, the fixed point. That's a great question. So the question, let me rephrase your question. The question is, what is the relationship between communication complexity of total search problems that always have a succinct answer? And this is, in some sense, this was the motivation for studying this question. And what the total version of this problem says, and actually Aviad and Yaakov's result about Nash, says that there is an exponential separation between non-deterministic communication complexity and deterministic communication, even randomized communication complexity. So that's, I think, very interesting, because most of you know probably that for decision problems, the widest possible gap between deterministic communication complexity and non-deterministic is at most quadratic. So this is very interesting, because in this instance, what these works prove is that there's an exponential gap. And I think I think this is a very good question because the question of studying the complexity class of communication complexity of total search problems, there are many questions there. What is a complete, so to speak, problem in that class? What's going on there? Yeah, that's a very good question.